Part 1 left us with one factory and one uncomfortable question. Did we create a real family boundary, or did we only wrap the Rover code? There is one honest way to find out. We will add a complete orbiter family, choose the protocol at runtime, and leave MissionSession unchanged. The proof will have 3 observable results. A Rover drive must succeed. An orbiter rotation must succeed with its own protocol. And if a rotation reaches the Rover family, the Rover safety policy must block it before its encoder runs. Abstract factory creates a set of related objects without making the client name their concrete classes. The important word is set. Each product may be valid by itself, but the application needs products that follow the same family rules. Its defining characteristic is a stable boundary around the whole family. The participants are small. Abstract products describe the roles the client needs. Concrete products implement those roles for one family. The abstract factory exposes one creation method per role. A concrete factory returns the matching products. The client depends on the abstract roles and receives one factory. Typical use cases include platform-specific UI kits, device protocols, and storage providers whose related objects must agree. It works well when complete families vary, compatibility matters, and the client should keep one workflow. When not to use it is just as important. Avoid the extra structure when there is one stable implementation, when the objects vary independently, or when direct construction is already clear. Our client is MissionSession. It needs a command encoder, a telemetry decoder, and a safety policy. Rover and Orbiter implement those roles differently, so they form 2 product families. Runtime choice still has to happen somewhere. We could put family checks inside MissionSession, but that would mix construction with the mission workflow. We could choose all 3 products independently in program, but every caller could assemble a mismatched set. Instead, program will choose one factory. After that boundary, MissionSession will work only with abstractions. We are rebuilding the compact Part 1 family boundary first. The domain can name both choices, but only Rover has a concrete family. That gives us a running reference before the second family changes anything. Start with the values that cross the workflow. Mission kind names the 2 runtime choices, Rover and Orbiter. Mission operation names the 2 commands, drive and rotate. These enums describe the domain. They are not abstract factory participants. Mission command carries an operation and an integer value. Telemetry frame carries a protocol code and its reading. The 2 result records make safety and final output explicit. Next, define the 3 product roles. iCommand encoder turns a command into protocol text. iTelemetry decoder interprets a frame. iSafety policy decides whether a command is allowed. The family boundary comes last. iMission protocol factory reports a display name and creates one object for each role. Notice what is absent. There is no Rover or Orbiter branch in these contracts. The interface describes the shape of a complete family, not which family will be chosen. Build one concrete family in the same order as the contracts. The command product is Rover command encoder. Its switch expression accepts a positive drive command and writes the Rover wire format. The fallback returns an unsupported marker, although the safety policy should stop an invalid operation first. The telemetry product is Rover telemetry decoder. Code 7 means battery percentage. Any other code becomes an explicit unknown reading. The safety product is Rover safety policy. A drive value from 1 through 25 is accepted. A different drive distance receives a specific distance rejection. Any other operation receives an honest Rover policy rejection. Finally, type Rover protocol factory. It owns the Rover name and creates all three Rover products. This class is intentionally boring. Its value is that one object represents the complete family. Now rebuild the client that must survive the extension. MissionSession receives one iMission protocol factory through a primary constructor. The protocol's property rejects null and keeps the family boundary. Inside run, the client asks that one factory for an encoder, decoder, and safety policy. It evaluates safety before encoding. An allowed command reaches the encoder. A rejected command becomes blocked. Telemetry still goes through the decoder, and the result takes its family name from the same factory. This workflow knows the product roles, but it knows nothing about Rover. That is the condition we need to preserve. At the application edge, create a mission session with Rover protocol factory. Then create one battery frame and one 12-unit drive command. The local name result tells us this is the observable outcome of the workflow. Print the family, encoded command, telemetry, and safety reason on one readable line. This is direct composition of one complete family. It is correct and small. We are not refactoring it merely because a pattern exists. We need a second family before runtime choice becomes a real requirement. Run the baseline. The family is Rover, the command is encoded as RV drive 012, battery telemetry is decoded, and the safety policy accepts the distance. This line is our control result. When we add orbiter, the Rover behavior must remain recognizable and the client workflow must remain untouched. The new requirement is not simply another class. Orbiter needs a different command format, a different telemetry code, and a different safety range. Those three behaviors must arrive together. The extension test is precise. Add the complete orbiter row, choose either row at runtime, and do not edit MissionSession.cs. If family checks leak into that client, our earlier boundary was in the wrong place. The domain already names both choices. What is still missing is a concrete orbiter family behind the contracts that already exist. The first new product is Orbiter Command Encoder. It accepts rotate and produces an orbiter command with an explicit signed angle. An unsupported operation returns the orbiter marker instead of borrowing rover behavior. The second product is Orbiter Telemetry Decoder. In this protocol, code 12 represents solar output in watts. The same product role now has a genuinely different interpretation. The third product is Orbiter Safety Policy. Rotation from -45 through +45 degrees is accepted. Everything outside that range, including a drive command, is blocked. Complete the family with Orbiter Protocol Factory. Its name is Orbiter, and its 3 creation methods return only Orbiter products. We have added 4 concrete types, but the abstract factory contract and MissionSession remain exactly as they were. Only the application edge needs to know which concrete factory exists. Define a small scenario shape containing a label, a mission kind, a command, and telemetry. The collection expression holds 3 cases. The first case preserves the rover's success. The second pairs orbiter with an 18-degree rotation and solar telemetry. The third deliberately pairs rover with rotate. It will prove the rover safety boundary, not product family compatibility. Inside the loop, the factory variable receives 1 complete family from a switch expression on mission kind. Pass that factory to the same mission session, run the scenario, and print the result. The runtime branch ends at composition. No mission logic is duplicated, and no family branch appears inside the client. Run the final program. Rover still produces its drive command and battery reading. Orbiter produces OB, rotate, +018, decodes solar output, and accepts the angle. The third scenario chooses the rover factory, but sends rotate. Its policy returns blocked before rover command encoder can handle the command. That third line proves a separate rule. Abstract factory keeps the products from one chosen family together. The safety policy validates whether a command belongs to that family's domain. Construction compatibility and command validity reinforce each other, but they are not the same guarantee. Read the final structure from the outside in. Program knows both concrete factories because it is the composition root. The chosen factory creates a matching encoder, decoder, and safety policy. MissionSession receives only the factory contract and runs the same sequence for either family. Adding Orbiter was localized to its concrete products, its factory, the domain values, and the runtime mapping. The client did not acquire an orbiter branch. That is the extension property we set out to test. Abstract factory favors one direction of change. Adding a complete family is localized. Implement the existing product roles and one concrete factory. Adding a new product role is expensive because the abstract factory and every concrete factory must change. There is also a limit to the type level guarantee. The interfaces require each factory to return the right product shapes, but a badly implemented concrete factory could still return semantically mismatched objects. Contract tests should run the same family coherence checks against every factory. Use this pattern when products must vary together, and callers should not assemble them independently. Keep direct construction when there is one family, or direct injection when products are intentionally replaceable one at a time. Part 1 moved construction behind one family boundary. Part 2 proved why that boundary matters. Rover and Orbiter encode commands, interpret telemetry, and enforce safety in different ways, while MissionSession keeps the same workflow. The runtime switch lives at the composition root, where concrete choices belong. The blocked case gives us the final distinction. The factory keeps a family together, and the family's safety policy decides whether a command is valid. That is abstract factory in motion. Choose one family, receive its related products, and keep the client focused on work rather than construction.